Welcome everyone to another episode Data with Nikk the Greek. And as always in this series, we're gonna talk about loading big data efficiently. And today we're gonna talk about a special problem within Spark, the small file problem. So meaning you have very small files in your storage and you want to process them, and then you realize, okay, Spark cannot really handle it. Something's going very slow, and so those issues usually happen if you have a REST API where you periodically save those small JSONs which the REST API returns, or if you have a real-time messaging service like Kafka where you receive very small JSONs or other files. And today we're gonna talk about how you can deal with it. So sometimes you cannot avoid it, but there are like some options how you can deal with it, how to make your processes more efficient. And out of experience, I have seen it quite often already. So you cannot even sometimes avoid to have small files, but you can deal with it as good as possible. And before we're gonna start, as always, if you like this channel, if you want to stay tuned with other videos, please subscribe below, and there gonna be a lot of more videos coming on. So let's get started. Before we're gonna jump to the small file problem, let's just have a very short recap of the Spark architecture. And if you see this for the first time, you're gonna find here above a link where you can see the full video explain the Spark architecture and the basics. So what's important is we have a driver and we have workers. And so we have a lot of small files in this case. So on the left side, you can see the incoming data sets. And what the driver generally is doing is it assigns data to partitions. So either you have bigger files and then they're usually split in smaller pieces, and then one piece is going to partition 1, one piece in partition 2. But with smaller files, the opposite happens. So a lot of small files which have maybe 10, 20, 100 rows of data, 1,000 rows of data sometimes, gonna be combined into one partition. And that's basically the assignment the driver is doing. And then it delegates the tasks to the worker, so the executor. So they are doing the heavy job at the end. And this means basically that those partitions are assigned to tasks. And it also creates an execution plan, and it saves the metadata of the files, etc. So all those things are coming into memory. And that's exactly where the problem is now caused. So if you have a lot of small files, all those metadata have to be stored in memory. And this, of course, might have some memory pressure, but also this might make already things slow. And then you have all the effort of queuing very small files. So you have to open the file, you have to close the file, you have to check for the storage and directories potentially, which the driver is also doing. And then you have the whole scheduling overhead. So instead of delegating, let's say, 10 files for a gigabyte of data, you have to suddenly delegate thousands or 10,000 of files. And you also know out of experience in real life, if you delegate and have too many things to do in parallel, it's of course also slow. And that's pretty much the issue we have also in Spark. And well, we also have a reduced parallelism because we suddenly have a lot of small partitions. So basically, there's an overhead cost in Spark. So basically, if the file is small, Spark is putting just a few files into one partition, and then suddenly you see instead of 8 partitions, which might be enough, you're gonna have 2,000 partitions. And that's something we're gonna see in a bit in the Spark UI in reality. And then we also have the serialization, deserialization. So yes, we have to serialize and deserialize them. And this comes also with a CPU cost. And so, well, what are we doing with it? So first of all, and that's something you're gonna find everywhere, increase the file size. Of course, this is not always possible, but at least the easiest way to deal with it, check the system which is providing the data, if there's a way to provide bigger chunks of data than smaller ones. Um, and if this is not possible, think about a process intermediate step where you can save the data um, in bigger chunks. So load 100 JSONs and then repartition them and save them in a Parquet table as intermediate step. One thing, for instance, what I like to do is I load the data, save it in Delta. We're gonna learn about Delta soon, and then we have a command which is called optimize. So it's bin packing the files together in smaller portions, and that's exactly what you want. And try to do in this intermediate step as less transformations as possible, just smaller files to bigger files, and then all those transformations, and especially wide transformations like joins, aggregations, don't do it with very small partitions. Then, of course, file formats like Parquet and Avro, which have less metadata, they're also compressed, have a benefit in the performance. And also, we saw that metadata has to be saved, and this is also like an overhead for Spark. So one option, as we learned in the previous episode, you gotta find also here a link, you can define the schema and have a performance benefit. And this performance benefit is to less metadata, schema in this case, to be processed. And then you can reduce the number of files per partition. So there's an overhead. If we manage per task less files at the executor level, it can also be faster. So instead of 1,000 files in one executor or one partition, we're gonna have then maybe 100, or 1,000 is nevertheless not possible except if you reduce this open cost in bytes parameter a lot. We're gonna talk about those parameters later, but basically you have two parameters where you can navigate how many data goes into one partition. So, and what are we doing today? So we're gonna have an experiment, and that's pretty much a similar one you saw in the previous video. So I'm gonna link the video here where we basically compare the performance with and without schema. So, and we have 10 million of rows. I'm gonna show you the data set in a second, where we have once 8 files and once 100,000 files. So that means 1.25 million rows per file versus 100 rows per file. And we do it for JSON, CSV, Parquet, and Avro. And we compare the loading times of having the same exact data in 8 files versus versus 100,000 files. And also like schema versus no schema, which reduces the metadata. So if you're looking on the file size, I just draw it down already. So we have JSON, for instance, with 1,218 megabytes. And then if you have small files, we have 12.47 kilobytes. And in the big file size, we had 152 megabytes. And you also see the writing time is already significantly slower compared to writing big files. And then you see in Avro, we have even 0.71 kilobyte files, which really Spark doesn't like it. So let's have a look into VS Code. So this is our favorite data set. We have an ID which continues, we have a date timestamp, and then we have like a string representation of the ID and then the first and second character. But how the data set looks today, it doesn't really matter. And what we're gonna be doing, let's go through JSON as an example. So we wrote the data, that's not relevant for us, but we read the data first of all without schema, the small and the big file. And then we use the auto-generated schema. So in JSON and CSV, the auto-interfered schema is a little bit different than the actual target schema, which we defined in the data frame. So as the target schema performs some kind of transformation additionally, I put it as a separate experiment. If you want to learn more, again, I'm gonna add the link here above in the screen. And basically, if you have a JSON and see like a timestamp, which is marked as a string, you usually can load it anyways as a string and do the casting later. And if you define the target schema to be as a timestamp, it does the casting for you directly. And that's why it's a slide transformation. And JSON, for instance, cannot deal with a timestamp. That's why it's returned as a string. So here we do the same thing with the target schema. So before we look into the Spark UI, let's have a look on the results. So how does it look like? And you directly see the results are impressive. So first of all, we have here the JSON loading times without schema and with schema. So we see we have here some meta information where the schema interference happens and then the actual loading time. So, and this part of the metadata and the schema takes a long time. Actually, I did another experiment here. I think this value I have to, no, I think this value I have to correct. So, and if you have like the big file, you see 6 seconds. But if you define a schema, you see a significant reduction because this very heavy task of interfering the schema disappears. And we see exactly the same thing for CSV, 7.7 minutes here as well, versus 5.8 minutes, 5.1 minutes. And then with schema definition, we see a significant reduction. And we are also closer to the total time which we have without schema. So you can see, for instance, here 7.7 versus 6 seconds, and then 18 seconds versus 3 seconds. Meaning, if you're gonna check the reduction by just doing those small things. So for instance, if you define the schema for a small file, you have reductions of loading time between 91 and 96%. Of course, if you have now, even with schema defined, and have bigger files, you see that there is a 99% with schema defined, 83% difference of the data load. So this means that a large file is 99% faster without schema definition than a lot of small files. So, and now let's have a look into the Spark UI. Okay, we are now in the Spark UI and let's observe what happens in those experiments. So what we had first is we had small JSONs which we load without schema. So here we see something listing leaf files. So that's something Spark's doing in the background to check if files and directories are existing and listing them. Here the job apparently, this process took so long that it actually created a separate job for it. I'm not seeing that often. And then we have the schema interference and then the actual loading of the data. And then the same thing, schema interference and the loading of the data. So, and what you can see here now is that this part here takes a lot of time with small files. So with a large file it takes 2 seconds, here takes a lot of time. The second thing what you can see is we have less parallelization because we have a lot of partitions. That means per partition we don't have a lot of data. So that means schema and the partitions are the issues which we can see, because later on you see here 19 seconds with schema defined, 23 seconds with schema defined. So you already see it's faster. Those meta topic is not there anymore, but our issue here with the number of partitions is still there. And let's have a look a little bit deeper into it. So let's go now with the schema defined process and check what's the difference. So here we have the one with the big files. So we see 1218 megabytes, and each one has between 150 and 152 megabytes of data and 1.25 million of rows. So well distributed and a good prioritization, because usually you say you want 2 to 4 times of partitions compared to the number of cores you have. And we have 4 cores in this case. That's why we see 4 tasks are always executed in parallel. But and also we have here the schedule and delay and the deserialization time, but you barely can see them. So they are quite insignificant in this case. But when you're looking here, we can first of all see that we have significantly less data which we process, as already assumed, because we have more partitions, and of course also the size of those data sets is then smaller. So basically, we are processing 379 to 400 kilobyte chunks. And we can see that percentage-wise, we have a significant scheduler overhead. So there's a delay until a task is scheduled. We have some task serialization. We can see here, for instance, that the serialization took even longer, and also like result serialization time, where the data is saved again. Um, well, took also some overhead. And that's basically the issues shown in the Spark UI um, of having small files. So in short, um, uh, bigger files are faster, and schema definition can lead, or not can, leads to less metadata to be loaded, and by that you can reduce your time. All right, now we said before that another option to overcome the small file issue is to reduce the number of files per partition. So, and there are two configurations basically, because we want to overcome that we're gonna have too much effort per partition to load and process too many files. That's the goal. And now we have the max partition size, which you can configure. In this defaults to 128 megabytes. And as the name already says, it's like the maximum amount of data which can go into one partition. So if you have a file which is 128 megabytes, or well, there's something more about it, but let's say you have four files, each 128 megabytes. Every file gonna go into one partition. Why I was stacking? So a default, it's also there's also another parameter defaulting to the number of cores you have. So even if you have a paquet file 128 megabytes, it might be splitted into smaller chunks, depending on how the file is constructed, if it's further splitted, and so on. Open cost per bytes instead is like a cost which is added to a file. So basically it says to load a small file, it's gonna cost me that much time, assuming that my file is 4 megabytes bigger. So that means if we have now kilobyte files, and in total the file size is 128 megabytes, it will not go all into one partition, um, even if it's below this value. Because to each file, there gonna be this open cost added, so those 4 megabytes. That means roughly, so 128 divided by 4, it's 32, so roughly 32 files, maybe 31, if you're gonna add those kilobytes up, would fit into one partition. And if you now have a small file problem, you have not two options. Either you reduce the max partition size or the open cost. And I wouldn't use, so that's actually the only case where I would recommend, okay, rather tackle the open cost per bytes, at least the most common one. Because imagine, normally you have like a mixture of small files and also bigger chunks. So imagine now you have a 50 megabyte file in between your kilobyte files, and then you have the max partition size reduced to 40 megabytes. What happens? You split this amazingly nice big chunk of file, which you usually otherwise don't have in the files, into multiple partitions. What you want to avoid is just to have too many small files or a lower number of files. So rather increase the open cost per bytes to, let's say, 8. Then your big file still suits into one partition, but your smaller files gonna be less per partition. And that's what we're gonna do now as an experiment. So let's jump to VS Code. I ran it now for JSON. So basically what I did is I created a function where I set the parameter. Let's jump to the function shortly. So it's here, so open cost per bytes. I take it as megabytes because it's easier to calculate. Then I'm rounding to rounding so that it's not decimal. And then I'm saving it as, here as bytes by setting the open cost in bytes. And then let's go back to or experiment. So basically what I'm doing is I go for 1, 2, 4, 6, 8, and 10 megabytes and execute then my experiment. Here for JSON, okay, I called it here also Avro, and I also have done this for Avro. So now let's have a look into the Spark UI and see what's happening there. So let's go here and now let's take, so first of all, what you can observe here is as higher the open cost in megabytes, as more partitions we have. So a small cost reduce the partition, high cost increases the partition. And that's exactly what we want to achieve. That higher number of partition can be better. So what we now see is here with 1 or 2 megabytes, it's quite high. Then we have an area 4, 6, 8 megabytes where we have a very good duration. And then when you are setting the open cost too high, it gets again quite slow. So, and I assume the 4 megabytes have been experimented a lot. So I assume 32, 31 files is the optimal number which Spark usually can process. But there are examples where it can have an influence where you can further adjust it. And when we are now opening those three, let's see what's happening here. So let's start with the 1 megabyte. So you can see we have here quite nice tasks, no scheduler delay and task visualization time, which you can observe here. We have 1.7 megabyte, but it takes like 2 to 4 seconds to process each file. So seems quite slow for those kind of data, and that's probably due to the overhead that they have to open all those files, process them, close them again, etc. Then if we're gonna go now with our perfect one, which takes only 22 seconds, let's open this as well. We see that the tasks take only milliseconds now here, and that's perfect. Of course, we see some scheduler delay, because we have now more partitions and thus more tasks which have to be scheduled, but still this delay isn't that bad compared to the long process time which we had with 1 megabyte. And now let's go to the 10 megabytes. So there we have even more partitions, and now the scheduler time seems to become bigger. So you can see the execution time is even lower. Okay, we have again like double the number of tasks, but here we have like here we suddenly have like one error where I don't know, the scheduling took too long. So this can happen. So in this case, it was probably this one which had like a significant influence. Actually, I don't think that this was only the only influence, but it sums up and becomes more complicated than if you're having a lot of partitions to process. So you cannot say that you just increase the max partitions to the limit, but you need like an area which is good. Usually 4 megabytes is a quite well-defined one, but sometimes if you have a lot of small files, you might want to go a little bit further up. Maybe there are also cases where you want to go a little bit further down if you have quite big or medium chunks of data. So that means let's go back to our presentation. So here summarize the results also for Avro. So we have like an area where it's quite fast. So in my experiment, it was a little bit different, 2.6 megabytes. Where bigger now it was like rather around 4, 6, and 8 megabytes, which had a faster processing time. So there are always some discrepancies. And especially compared to without schema and 4 megabytes, which is the default value, you can see 7.7 a minute. So with all those options, you really manage to get now way faster time. So 41 versus 5.1 minutes, or 7.7 versus 21 seconds. And that's like like a really good speed perform improvement. And to summarize what we saw today, so we saw that bigger files are faster than smaller files. And you should find a solution, if possible, to make the files bigger. Defining the schema can reduce, especially for smaller files, the overhead significantly for the metadata. And then the last thing we saw just right now is that open costed bytes can influence the loading time by adding overhead cost to the file sizes. And this reduces, of course, the number of files per partition, or it increases the number of partitions we have. And with that, thanks a lot for watching today. I hope you enjoyed the video. If you want to see more of that, please subscribe to my channel below, and we see each other in the next episode.